Hi, Zach. I hope you're doing well. I just saw your email about mapping pixels to your POV display. I have some thoughts on that. It is. I don't think it's going to be as difficult as you might think. There's really not a whole lot of difference between mapping the text characters to the pixel coordinates on this, and how to map pixel values to your POV display. Okay, the main thing you're going to run into is your POV display doesn't. It isn't an XY display. It doesn't have uh, an X resolution along this axis and a Y resolution along this axis. It does have two axes, but one of them is a radius and the other one is an angle. So it's a polar coordinate system. So what you're going to have, your challenge here is going to be mapping your polar coordinate system to the 2D sort of Euclidean rectilinear coordinate system that you're used to working with. So I've mapped this out, like we've got a square rectilinear image here, with each of the little grid points being a pixel in the image. And then this represents one update arc, is what I'm calling it. So the update arc is one flash or one update of your LED strip. And I've mapped this out over here, sort of a sketch of what your arm or your propeller or whatever you want to call it can look like. So you've got your center point here, and this is going to be the point around which everything is revolving. Now, here's a little trick. You don't have to do it. The math isn't that much harder. Matter of fact, it's exactly the same math, but it's a little trick to double your effective resolution. So notice we've got our rotational point and a gap, and an LED and a gap, and an LED and a gap, and an LED and a gap, and so on. Then on the other side of this pivot point, you have an LED, a gap, an LED, a gap, an LED, a gap. So what you do is you've actually ended up staggering these such that you've got gap LED on one side. On the other side, you have LED gap, LED gap, LED gap. So I think you had like 1 centimeter resolution, so a pixel per centimeter on the strip you've gotten. So if you do it this way, you effectively end up getting 1 pixel every 5 millimeters of update, and so spinning so quickly, that you're going to have the observer see a pixel in between each of these little gaps, which is effectively doubling your visual resolution. Okay. Sorry, something's got my allergies today. Probably this little space heater I've got up here. It's very effective in heating, but I think it's stirring up some dust. Anyway, so effectively what you're going to need to do is you've got your rectilinear image, and you've got these pixels that map to different locations in that image, and then you've got this pixel arc that is what you're going to be illuminating. Now, one thing you have to notice is that you've got a different kind of resolution. Your radial resolution, so going along the radius, is going to be defined by this guy, the pixel density of your wand. However, on the other axis, if you want to call it that, it's going to be your resolution, your angular resolution along your rotation. And this is going to be a factor or a function of how many times you can update your LED strip per revolution. And so this is going to depend on a couple things. One, it's going to depend on the RPM that you're spinning the LED strip. And the other factor is how many times can your microcontroller actually update those pixels per revolution. And I think you were using a Hall effect sensor instead of like an encoder to radial encoder to figure out where you are in the rotation. So in that case, if you're using a Hall effect sensor to just get like one sample of where it is in the rotation, these little pie slices are going to be approximated based on how long it takes you to make your revolution. So that's not the most accurate way to do it, but if it works, it works. And I'm pretty sure those little tiny fans we're looking at do the same thing. But now one of the frustrations here is notice that your pixels change shape as you get further and further from the center of rotation. And this is one of the weaknesses of a POV style display. So up here, your pixels are going to be much larger than your pixels here. As a matter of fact, if we look at it in terms of our grid paper, our pixels are going to, one pixel here is actually going to map to multiple pixels inside of your source image. And that's okay. There's a couple ways to handle that. What you could do is you could figure out all of the pixels that are encompassed inside of that part of the arc from your source image, and then average their colors together, and then set that LED to be that average color. I'm okay if you just pick the nearest pixel. So if say this is your arc, what you'll want to do is you'll probably know if you're rotating this way. You'll know this position here, so you're going to know what radius each of these pixels are, and you're going to know the angle that it has revolved, and you're going to know based on your measurements how long you can keep that pixel turned on for that arc. So you're going to know what this span is right here. And so since you know what the angle is and you know what the radius is for that pixel, just using sines and tangents, you can figure out what the XY coordinate within your source image should be. And then you can reference that pixel color and then write that to the LED while it's making that sweep of the arc. Yeah, let's just make sure. So, if we've got, if this is our hypotenuse, and this is the pixel we're wanting to sample, because that'll be in the middle of our arc, and we know what this angle is. That's so that would be sine of this angle, opposite hypotenuse. Yeah, you can use the sine of this angle to figure out what this is going to be, and then the tangent to figure out opposite over adjacent. Yeah, and then use your tangent to figure out what the y value is going to be. So your sine will get you your x value, and your tangent will get your y value in your source image. Now, that's one way to do it. That's doing it on the fly, but you can use the same mathematics to actually figure out, pre-compute, what these offsets and the color values at those offsets should be. So essentially, re-encoding your image to make sense for a radial display. I'm not saying do that. I'm saying do what's going to be most convenient for you, and we'll get you to the solution more quickly. But yeah, it shouldn't be too big of a deal to figure out which XY pixel maps to which arc pixel. Okay. What else? Oh yeah, since this is, your POV display is going to be radial, and you're mapping from a rectilinear source image, you're definitely going to have dead pixel areas. So, oh, hit the camera. Don't fall, camera. There we go. This is all very precariously balanced on the edge of my desk. Okay. So, you'll have dead pixel areas, so there will probably be pixels here in your source image that don't map to any radial location at all inside of your POV display, and that's okay. These are just pixels in the image that we're just not going to display. Yeah, I think that pretty much covers that. So if you have questions about the actual math, or you want to sit down and actually work out the mathematics of this, let me know. We can do that. But definitely going to be achievable using, just a little bit of trig, and knowing, your pixel density along your arm, and knowing the number of times you can flash those pixels on and off as you make a full rotation. Okay, so that's, yeah, I think that pretty much covers it. You're converting your XY resolution on the image into angle and radius resolution on your POV image. Yeah. Okay. Like I said, if you want to talk through this, let me know. We're living in a weird time. I don't know if I said this at the beginning of this or not, because, I don't remember anything anymore. This would normally be a conversation we would have in the lab, drawn out on the marker board, so it'd be easy for everybody to see and understand. But, we're making do with what we got. Okay, so if you need anything or have any questions, please let me know. Otherwise, I will see you on Friday.